In this video, we are going to discuss example 23, integration of an integrand x squared divided by a denominator in the form of square root of 9 minus x squared. In this kind of integration with a denominator in the square root of some constant minus x squared, we will have to use a trigonometric substitution in the form of x equals to a sine theta. To begin with the method to solve this integration, we first look at the expression in the square root. The square root expression can be mapped to a right triangle. Specifically, by looking at this expression and using the Pythagoras theorem, the square root looks like the expression of one of the sides of the right triangle with a hypotenuse of 3. This 3 is corresponding to the term 9, where 3 square gives you the 9, and x could be referring to either the height of the right triangle or the base of the right triangle. Either one identification is valid. You just have to choose where to label the x. Here we will choose to label the height as x instead of labeling the base as x. But I would like to remind you that if you label the base as x, the choice is also valid and you would also be able to be led to the correct answer, but with a slightly different algebra. Now, once we have labeled the hypotenuse and the height of x for the right triangle, we label the angle theta here and write down the relationship that relates hypotenuse, the height, and the angle theta. In order for me to generalize the method more easily later, I will label the hypotenuse to a and remind myself that a is taking a value of 3 for this particular integration. So I'm going to write down the relationship between the hypotenuse, the height, x, and the angle in the generic expression of a. But later I'm going to substitute a equals 3 back to my expression to obtain the full solution for this integration. The relationship between a, x, and theta is simple. That is, the height is just the hypotenuse times the sine of theta. This is the trigonometric substitution that is most crucial for this integration. Once this crucial triangle substitution is written down, then we can proceed to translate the integrations with respect to x into the integration with respect to theta. To this end, we need to know what is the expression of x squared dx and also the expression of the square root of a squared minus x squared. So x squared is just a squared sine squared theta. A squared minus x squared is just a squared times 1 minus sine squared theta, where I simply substitute the x squared from this expression. And this is nothing but just a squared times cos squared theta. Cos squared theta is identified to 1 minus sine squared theta. And then I'm going to take the square root of the expression, and this turned out to be a cos theta. Therefore, the expression of the square root term, which is this one, is simply expressed in terms of theta as a cos theta. Then we also need the expression for dx. Dx is obtained by referring to this substitution rule, which is just a cos theta d theta. So now we have all the expressions on the table, dx, the square root term, as well as the x squared term. So I'm going to write down here the expression for x squared dx, which is a squared sine squared theta. Dx is a cos theta d theta, whereas square root term is just a cos theta. So we cancel off the a expression and are left with a squared times sine squared theta d theta. Here the cos theta term also get cancelled off. To proceed with the integration of sine squared theta, we have to translate the integration of the square of a sine into a trigonometric function without a square. So we deploy the identity of cos 2 theta equals to 2 sine squared theta minus 1. This will allows us to express the square into the form of a function involving a trigonometric function of cos 2 theta without any power. That would simplify the integrations into the form of a much easier function to be integrated. So this is the integration of sine square theta. It could be straightforwardly written down as theta over half plus sine, here I have 2 theta plus an arbitrary constant. So the next thing I want to do is to translate the expression of theta and sine 2 theta back to the expression of x. The x and the angles were shown to be related to each other through the construction of an right triangle via Pythagoras theorem. This is the triangle that was constructed earlier. So from this right triangle, you can easily write down the expression for sine theta, which is x over a, and cos theta, which is square root of a square minus x square divided by a. We need the expression of sine theta and cos theta because we need the expression of sine 2 theta, where the sine 2 theta is related to sine theta and cos theta through this simple identity. And this is written as 2 times x over a times square root of a square minus x square divided by a. So we have a factor of a square in the denominator for the sine 2 theta. The angle theta is simply arcsine of x over a. So we have almost done with this integration. Here you have a square over 2 times arcsine of x over a plus a square over 2 times sine 2 theta, where sine 2 theta is simply this expression. So I'll simplify this further. There's a constant I was missing out. So this is the expression for the integration in terms of a, and now I'm going to substitute back the values of a equals to 3 in our present case. That would then give me 9 over 2 arcsine of x over 3 plus x times square root of 9 minus x squared plus an constant of c. I'm sorry, I think I was making a mistake while performing the integrations for the term cos 2 theta over 2. Here, I should have a factor of 4 instead of 2 due to the presence of this factor 2 and the 2 in the cos of 2 theta. So I have to make some corrections. There's a factor of 2 here, and this would be a factor of 4. So there's a factor of 2, a factor of 2 here as well. Okay, so that is our solution to the integrations of example 23. You just need to be slightly careful when you perform the integrations. So I made a mistake and I have corrected it. As a conclusion to this video, we have performed the integrations of this integrand. The characteristics of this integrand is that it has a denominator in the form of a square root of the difference between a constant and the square of a variable x. You map the square root expression to a right triangle using Pythagoras theorem. Specifically, you realize that this 9 is the square of the hypotenuse, where x is one of the sides of the triangle. You can choose to label the x as the height or the base of the right triangle. Either way is a valid choice. Here we choose to label the height as x. Once the labeling of a and x is done, we label the angle theta and write down the substitution rule that relates a, x, and theta. With this substitution rule, we can then translate the integrations with respect to x into the integration with respect to theta. After some trigonometric and simple algebra, you can then pass the integrations in terms of x into the integration in terms of theta, which is easily integrated to give you the expressions of theta and sine 2 theta. You can then translate the theta and sine 2 theta back to the expression of x by again referring to the triangle you constructed earlier on. That is how you solve these integrations of example 23.